Okay, so hello everyone. My name is Juho Nurminen, and this is app.setAsDefaultRCEClient. For the next 45 minutes or so, I'm going to be talking to you a little bit about Electron and exploiting scheme handlers to gain code execution in apps. This talk is based on research I did in early 2019 and first presented at Zero Nights in November, though the content has been slightly updated since. Most of the vulnerabilities I'll be talking about have already been fixed, often even before I ran into them myself. But what's interesting is that Electron hasn't really published any advisories about them. Developers mostly aren't aware that any issues ever existed, so outdated versions are still out there and being used in apps. In the name of transparency, I should also mention that since doing this research, I've joined the product security team of one of the apps featured in this talk. So there's sort of a conflict of interest there, but that hasn't really affected the content of this talk since the research took place before that actually happened. Let's start off with a quick introduction to Electron and muon. That may sound like nuclear physics, but the only thing really that those two have in common with that is the end result if you don't know what you're doing. I'll demonstrate that a bit later on. Anyway, no one likes a nuclear meltdown. If you're not familiar with Electron, it's a desktop application framework. It lets you write cross-platform applications using web technologies like HTML and JavaScript. Without oversimplifying too much, it's basically just the Chrome browser bundled with Node.js and some extra JavaScript APIs. Then there's muon, which is just a fork of Electron. It was started by the Brave browser as a framework to use in that. And the unfortunate thing about it is that while it started off as an effort to harden the Electron framework against attacks, it's since been abandoned and deprecated, and it's no longer being updated. So it's hopelessly out of date and full of vulnerabilities. While Electron is definitely more popular of those two, muon still has its users, so those users aren't getting any security patches. Anyway, a while back, in 2018, Electron published a CVE, conveniently named CVE 2018-10006. It's a remote code execution vulnerability affecting Windows. And at the root of it is an API call named app.setAsDefaultProtocolClient. Invoking that function, as the name would suggest, registers your application as the default scheme handler for a particular URI scheme. You could use it, for example, to set your application as the default mail-to handler for email links. Or you could register a custom scheme in order to support deep linking in your chat app. That actually seems like one of the most common use cases for that. The way the API actually does its trick on Windows is through the Windows registry. It looks up a key matching the URI scheme and then sets the corresponding value to point to the executable. And the way the executable gets the URI itself is through a simple format string that's used for the command line invocation. So in this example, %1 is simply replaced with the URI as is. That means if the URI contains any special characters, namely spaces or double quotes, you end up actually injecting command line switches to the executable itself. How that actually impacts the application obviously depends on which command line switches the application supports. But in the case of CVE 2018-1,006,000, it turned out that there was a command line switch which directly allowed command execution. In practice, the way it would work is you'd have a crafted link like this one, pointing to the vulnerable URI scheme of your app. The URI contains a double quote, a space, and then the --GPU-launcher switch. All that needs to happen is for a user to click on the link on a machine that has the vulnerable app installed. And like magic, Windows executes any commands you injected. So calculator pops up. This was obviously patched way back in 2018, hence the CVE. Somewhat interesting, though, is the way Electron decided to approach the patching. The original patch was nothing more than a huge blacklist of all known command line switches. More than 1,300 of those switches, which would just then be compared against the command line invocation of the application. If both the URI and a blacklisted switch were present, then the app would just crash itself. Now, obviously, this wasn't enough. I wouldn't be giving this talk if it was. There have been several bypasses, some by me, some by other people, and there will probably continue to be more. Let's look at some of those bypasses in just a moment. But before I get to the actual meat of the presentation, I'd just like to credit a couple of other researchers who have worked on this before me. This isn't a comprehensive list by any means, and if you feel like you should be on it, let me know. But here are some links that you might want to look at if you want to dive deeper after this talk. The people at DoyenSec were probably the first ones to bypass the fix to CVE 2018-1,006,000. And a write-up of that is available on their blog. The same people also publish a tool to help secure Electron apps, so if you're working with those, look it up. It's called Electronegativity, and it's really worth a look. I also have to thank Luca Caratoni, a co-founder of DoyenSec personally, for providing me with some very helpful feedback on this talk. There was a very cool talk about modern desktop applications at Infiltrate 2019, presented by Thomas Shadwell. The scope of that talk was a bit wider than mine is here, but if you're interested, go look it up. It's available on Vimeo. And then there's a talk by Andreas Lind from way back 2016, where he talks about hacking Mattermost, one of the apps also affected here. That's available on YouTube. Anyway, back to the actual topic. As it turns out, in February 2019, plenty of apps were still vulnerable to something awfully similar to CVE 2018-1,006,000. And what I have for you is 3 separate cases, examples of those, 2 specific to certain applications, and 1 more generic that was affecting Electron as a whole. Let's start from the top. So, Mattermost. Mattermost is a chat app, sort of like Slack, but open source. And like Slack, it has a desktop client built on top of Electron. There were three things in Mattermost that led to RCE. First of all, the Mattermost desktop client has this command line switch, which allows the user to specify a custom data directory. This is where the application stores all its local data, including caches and configuration files. There was no real bug here, but it's an essential part of the exploit. Secondly, because we're talking about Windows here, universal naming convention is supported. UNC is just a different way of specifying file system paths on Windows, but it comes with a twist. Whereas regular file system paths only allow you to specify local paths, file system UNC paths allow you to also specify SMB shares on a network, even if you don't really have those mounted, so to speak. Microsoft often refers to UNC paths as network paths. Thirdly, the app was loading configuration files in an insecure way, which allowed those configuration files to execute code. Unlike the previous two, this one was actually a bug and has now been fixed. Mattermost has also implemented some additional mitigations against this, but I won't bore you with the details of those. So these are screenshots of the Mattermost desktop client code, source code, from the vulnerable version. And at the top, you can see how the code is accessing a file named boundsinfo.json, which it's then parsing using the native JSON parser. And at the bottom, which is part of the same file, it's passing that resulting JavaScript object to the browser window constructor. That's part of the Electron API. And there was no validation in between. The idea of that was just to set the dimensions of a newly created browser window so that when you close the application, it would reopen with the same sized window. Simple feature, but surprisingly broken. So if you look at the Electron documentation for browser window, there's something slightly concerning there. The options object, which we just saw getting loaded from a file and passed to the constructor, it does let you configure the dimensions of the window, sure, but there's also lots of other things. In particular, there's an optional property named web preferences, which in turn has an optional property named preload. And the description for that property says that any script specified in it is automatically executed, which sort of sounds bad. But what's worse is that it's executed with access to Node.js APIs, regardless of the access level of the browser window itself. Access to Node.js APIs means code execution, native code execution, which is bad. So to put it all together, we start with a crafted URI again. The URI again contains a double quote, a space, and the injected command line switch, which then references an attacker-controlled server via UNC. When a user clicks on this link, the app starts reading and writing configuration files on the attacker-controlled server. So the files aren't local, as you'd expect, but they're accessed over SMB. The boundsinfo.json file is loaded, and it, in turn, references a script. That script is handed over to Node.js, which means code execution. The next step, unfortunately, I can't tell you what it is. I know it's been a year since I did this research. They still didn't fix the application in time. Mainly, I guess, because the application was based on Muon, which is the deprecated framework, which is not getting updates anymore, and migrating away from an entire framework is a huge hassle. So I'm not going to name the application, but I am going to tell you about the technical details of the exploit. This is very similar to the previous one. This app also had a command line switch for specifying a user data directory. It also supported UNC paths, but what it did not have is a way to execute code from the user data directory. So the approach for that, the approach that I used in the previous exploit didn't work here. I had to come up with something else. Interestingly, the app was using PowerShell to do some cleanup tasks in the user data directory. And that meant passing the path to PowerShell. And that's where UNC turned out really handy. Windows is fairly strict when it comes to naming files in the file system. So if you've already successfully accessed a file previously on a local file system, you can make fairly strong assumptions about the name of that file. For example, you can pretty safely assume that the name of the local file won't contain a double quote and won't contain the dollar symbol, because those aren't allowed in a Windows file system. But what if your file system isn't local? What if it's on a network share, on an SMB share, and the SMB share is a Linux server? Suddenly, those assumptions about the naming of the files no longer hold. So this is a screenshot of the cleanup code, the task that the application was doing in the user data directory. This is taken from the debugger, but I've had to slightly alter the code so as not to reveal the name of the application. It's pretty easy to spot the injection vulnerability here. Since user data, the name of the directory, is passed directly to a PowerShell command. But this wouldn't be vulnerable or exploitable if only local paths were allowed, because the path is accessed already before in the code. And if it's not a functional path, then the app would just crash. So local paths can't contain double quotes or the dollar symbol, but UNC paths can. So let's exploit this one. Starting with the crafted URI again, we inject a user data path. But this time, the path itself also contains an injection. We have a dollar symbol and calc.exe there, directly in the path. When you click on this link, the application starts accessing configuration files. And if it can't access those, then it crashes. That's why we still need the SMB server on the other end. But once the configuration files have been loaded, at a later point, the path is then passed to PowerShell. And because of the nice little dollar symbol up there, I own you again. So these two examples were just specific to single applications. But now for the third one, Electron had a bigger problem. It's common convention for command line interfaces to stop parsing additional command line switches after they encounter 2 dashes and a space. And Electron is no exception. So in fact, one of the official workarounds to CVE 2018-1,006,000 was to include those 2 dashes in your invocation of the API call, because that would prevent an attacker from injecting additional parameters to the end of the command line. Because the official patch, original patch to CVE 2018-1,006,000 was based on a blacklist compared against the command line invocation, it also makes sense to stop processing that blacklist after you encounter those 2 dashes in the command line invocation, right? Well, it would make sense if Electron was just made up of Chromium and nothing else. Unfortunately, there's also Node.js, which for some reason doesn't respect those 2 dashes. So Node.js would continue processing all command line switches even after the 2-dash delimiter, all the way to the very end. Here's a close-up of the blacklist you already saw in an earlier slide. See the problem? There are 2 blacklisted node switches, inspect and inspect BRK, which enable remote debugging. They're Node.js switches, so they don't respect the delimiter, yet processing the blacklist stops at the delimiter. This was actually fixed in Electron already by the time I came across it. The patch is included in Electron 3.0 and has been backported to 2.0.9. But the 3.0 release doesn't mention the fix at all. The pull request is explicitly tagged as no notes, meaning that it won't include the notes from that PR. And the 2.0.9 release notes only refer to it as an additional fix to something related to DNS rebinding, which doesn't really make sense at all. So it's not surprising you still find this issue exploitable in apps half a year later. And boy, was it easy to exploit. I went through the Electron app directory. They keep this directory of apps that are implemented using Electron. And I picked out just the most credible looking apps, ran some scripts, and ended up with RCEs in VK Messenger, Postman, the app I can't name yet, Hyper, which is an Electron-based terminal emulator, Missive, which is another email app. And by no means did I comb through everything. There are hundreds of apps in the app directory, and I might have looked at 20 or so. So there are probably vulnerable ones still out there. One more time, let's go through the exploit flow. Again, we start with a URI. This one is for VK Messenger, as you can see from the scheme. There's a double quote, a space, 2 dashes, and then the inspect switch. We're binding the debugger to all IP addresses to make it public. The value of the inspect switch gets passed to the Node.js debugger. It starts listening on TCP 5858 for incoming connections and just waiting for one to arrive. The attacker on a remote machine connects using the Chrome DevTools protocol to the debugger. And that's it. The debugger gives the attacker full access to all Node.js APIs, and it's trivial to launch any command. So, demo time. I have a live demo of 2 specific applications, which I'll bring onto the screen in just a few seconds. So I have a demo of two applications. One of them is Mattermost, and the other one is VK Messenger. Let's start with Mattermost. I have two VMs. This is a Kali Linux VM, which stands in for an attacker-controlled Linux server. And then I have a Windows VM, which stands in for the victim. On the Linux VM, I have an SMB server. Here's the SMB configuration. I have a share named Mattermost, pointing to a directory named Mattermost. And it's public, and it's writable, and it's guest accessible. In the directory named Mattermost, I have a bunch of files. Most interestingly, I have a bounce.info JSON file here, and I have a payload file over here. If I look at the bounce.info JSON file, we can see that it's referencing the payload file, and it's a very simple file. We can also look at the payload, which is equally very simple. It's just requiring the child process object and then executing calculate.exe. So to start the attack, we have a malicious web page. This could be hosted anywhere online, and it contains a link which is pointing to Mattermost. When I click on the link, Edge will tell me that, OK, you're trying to open Mattermost. Do you really want to do that? But if we're assuming that the user is actively trying to open a chat window, then sure, this would be perfectly fine. Let's click yes. Mattermost launches, and the calculator launches. So that's not supposed to happen. What's happening in the background is that the application is connecting to the Linux server, loading the config file, then loading the payload file and executing the contents. And executing, well, the calculator. The other demo I have is for VK Messenger. And that works a bit differently, since that's the Electron issue, which uses the debugger. Again, I have a link here, which points to the VK Messenger application. This looks very similar to the Mattermost flow, except at this point, nothing happens. I just open the application regularly. But now, as an attacker, I can go to my remote host and call a script connecting to my victim host and executing a command. Now, before I execute that, let's bring up that window so you can see it. Executing that launches the calculator on the other VM. And that's just simply connecting to the Node.js debugger and calling a simple script in the background. So in the VK Messenger demo there, you might have noticed that I was using a custom script to invoke the debugger. That's actually just a tiny wrapper I wrote around Chrome Remote Interface, which is a JavaScript library for using the Chrome DevTools API or the Chrome DevTools protocol. You could obviously do the same thing using the DevTools integrated to the Chrome browser itself, but using the command line is a bit quicker, especially if you have to test multiple applications in a row. The tool is available on GitHub, and you can find it in my profile, or you can grab the URL from there, but that's not going to be trivial since it's a hash. Anyway, my work obviously didn't end when I managed to pwn all the Electron apps. Someone had to fix those issues, and that meant coordinating disclosure and communicating with vendors. I tried to find the easy way out and just ended up doing twice the amount of work. Here's a few lessons from that. So as I mentioned, this all started in February 2019. I was casually poking at one app, which happened to be Mattermost, when suddenly all hell broke loose and I had 7 RCEs in 6 different apps. Disclosing all of those privately, one by one, would have been a huge effort, especially when most vendors still don't publish proper security contacts on their websites and don't necessarily even behave politely towards researchers. So I wanted to come up with a way to somehow do this better and more coordinated. The obvious solution was to use Trend Micro's zero-day initiative. ZDI buys research and responsibly discloses it to vendors. That would allow me to report all the issues to a single point of contact and have them take care of the further reporting. So that's what I did. I submitted my reports to ZDI at the end of February, and just a couple of days later, I already got a response. It wasn't exactly what I was hoping for, though. Without even looking at the vulnerabilities or exploits, ZDI had determined that 5 out of the 6 apps were simply not interesting to them. They wouldn't buy anything related to those apps. But they didn't say anything about VK Messenger, presumably because that was still interesting enough. So the initial response was super quick. Unfortunately, the process from there on was exactly the opposite. It was complete radio silence from ZDI for the next whole 3 months. And what was more disappointing was the response when I finally got it in June. ZDI had tested the exploit against VK Messenger and determined that, no, it doesn't work. What had happened is that VK Messenger had already updated their Electron version, and ZDI was testing against the latest release of VK Messenger. So it wasn't vulnerable to the -- command line issue. So since ZDI turned out to be a dead end, I had to retest everything, because it had already been 3 months, and it could be that others have also upgraded their frameworks. Luckily they had, because otherwise I would have ended up doing a whole lot of work. So I only ended up having to contact the app I couldn't name yet, and Mattermost, and one other app. And Mattermost actually ended up hiring me as a result of this, so all's well that ends well. I have not been in contact with anyone on the Electron side of things, but they've done quite a bit in regard to further patching CVE 2018-1,006 since it was first published. The original blacklist of 1,300 command line switches has been updated. It was something else for a while, and now it's 0 switches. It's not used anymore at all. They're now using a different approach entirely. They've also twice changed the way they handle command line switches in general. And the good news is that I'm not currently aware of any way to directly exploit CVE 2018-1,006. The bad news is that Electron still hasn't really addressed the root cause in any way. URI handlers are still registered in exactly the same way. And although Windows is partially to blame here, there are things that could be done in the framework as well. Electron has also not published any advisories, even hinting that the original patch to CVE 2018-1,006 was not sufficient. So this is basically the only place you're going to hear that. Microsoft has done some things to address this general issue too. The main one is that if you use an up-to-date version of Internet Explorer or Edge, you will no longer be able to open those malicious links because the special characters will get URL encoded. That didn't used to be the case. You can still open those links from other apps though. So if you have a chat app that can link to itself, then you could still have a vulnerability. For the developers and security people who are probably here in the audience, there's a couple of interesting takeaways from this. First of all, keep in mind that the app.SetAsDefaultProtocolClient API is a dangerous one. And scheme handlers in general are dangerous. If you find yourself using those, think twice. Do you really need them? And if you do need them, are you using them correctly? Are you sanitizing command line parameters? Or somehow preventing them from being injected? Secondly, UNC and other platform-specific features can have unexpected effects when you don't account for them. Even if you're working on cross-platform apps using a platform-independent framework, you should always try to be aware of the underlying platform itself and the features available therein. Otherwise, you might end up shooting yourself in the foot. And finally, Electron has a bad habit of not publishing security issues and informing developers about them. So it's critical to keep your frameworks updated even when there's no CVE to panic over. Since May last year, Electron has also migrated to a 12-week release cycle to keep up with the 6-week cycle Chromium uses. So when they only support the 3 last major releases, if you now release an application based on Electron, that means you have to release another version after 8 months at the latest, just to update Electron and to keep up with the supported versions. That's it for me. I think we have some time for questions, so thanks for your time.